So in this video, we're going to start looking at a new form of a quadratic graph called vertex form. And we're going to look at how this vertex form with its values of a, h, and k actually impact our parent graph of y equals x squared. So if we look at our new form here, we can see that we have x being added with h inside the parentheses, and then the quantity is squared, multiplied by a out in front, and then k is added off on the sides. We're going to look at how a, h, and k impact that parent graph, and we're going to start by looking at the value a. So if we go and we look at our calculator here, we can see that in black, we have our parent graph of y equals x squared, and here in red, we have our new transformed graph where we are going to change the values of a, h, and k and see how they transform our parent quadratic graph. So here, if we start with a, we notice that by default, a is set to 1. And if we start to move a around, so say we make a 2 or 3 or 4, what we start to see is that that graph becomes skinnier and skinnier and skinnier. And what's really happening here is we're taking every single point of y equals x squared and we're multiplying it by 6. And what that does is it takes every single point and it stretches it up to be 6 times its height. And if you think about yourself as a human being, if we took our height and we multiplied it by 6, we would also get very, very skinny and very, very tall. So that's what's happening here is our graph is being stretched up. And so in math terms, this is called a vertical stretch. We are stretching the graph by making our a value 6. Then from here, if we change a and we make it something a little bit smaller, like 0.5, notice here that our graph got a little bit wider. It now looks a little bit fatter, it looks a little bit shorter, and that's because we're taking every value of y equals x squared and we're multiplying it by 0.5. We are shrinking it down to half of its height. We're making it shorter, it's being shrunk down. So this is called a vertical shrink. So we can stretch our graph up by giving it an a value with a distance from 0 of more than 1, and we can shrink it down by giving it a value between 0 and 1. And then from here, as you just saw, when a becomes negative, it flips it over the x-axis, or it's called a vertical flip. So a here is called our stretch factor, and it can do 3 things. It can stretch our graph up, it can shrink our graph down and make it shorter, or it can vertically flip our graph over the x-axis when a becomes negative. So that's how a impacts our graph. Now from here, if we look at k, notice that k is by default set to 0 here. And if we start to move k up, remember k is the value being added on the outside here, k starts to move our graph vertically up. And so this doesn't stretch, shrink, or flip our graph, but it does vertically shift our graph. So it's called a vertical shift. And this k value on the outside moves our graph up and moves our graph down. And then here, hopefully you're starting to make a prediction about h. H, that value inside of those parentheses, that would be value being added there, is our horizontal shift. So notice the graph doesn't change shape, it just shifts left and right. And here what I want you to also notice is that when k was positive, k went up. When k was negative, k went down, kind of as we expected as a vertical shift. But when h becomes positive, it shifts to the left. And when a becomes negative, h becomes negative, it shifts to the right. So it kind of does the opposite of what we would expect here. We're going to make notes of this on our slides. So if I go here, we're going to go and we're going to focus on a first. Remember when a had a value, a distance from 0 more than 1. So we're going to change this a little here. This was called a vertical stretch. And it would essentially make our graph skinnier and make it taller. When a was a value that was trapped between 0 and 1, the distance from 0 wise, we had what was called a